Hi, hello everyone. In this lecture today, we continue integrated optical components, and in the previous lecture we discussed directional coupler, its transfer function, transfer matrix. Now we will be discussing DC based MZI, Magenta interferometer. You know, we have discussed earlier Magenta interferometer, but that is actually Y junction based. You have input waveguide and you have split it into two waveguides and then another combiner, and that is how Magenta interferometer, one by one Magenta interferometer we have discussed earlier. Now we want to discuss DC based Magenta interferometer, which will be two input ports, which will have two input ports and two output ports. And along with that, we will discuss about Microring Resonator, that is also designed with the help of directional coupler, whatever we have learned so far. So, that is why we will be concentrating on this MZI and Microring Resonator, specifically their transfer function, how it will look like for Magenta interferometer, and transfer function for unbalanced Magenta interferometer. We will learn what is balanced and unbalanced, and transfer function of a Microring Resonator. So, that is these three things we will be deriving the transfer function of these three important components heavily used for photonic integrated circuits. So, I want to give a bit of a recap of transfer function of a DC directional coupler. You have two input 1, input 2, in input 1 the field amplitude you are giving AI and BI. So, A, B are the inputs, I stand for inputs, and two output ports you will have A naught, B naught. Okay. And we know that this transfer matrix for a directional coupler, that is coupled to waveguide, we can summarize using this matrix. So, RR star and minus JT star, that we have derived earlier. And if we have a input output A naught B naught, we can use this transfer matrix to find out if we know the input and output, then we can find out what is the output amplitude with respect to their corresponding input values. This AI BI can be complex and they can have different initial phase, that does not matter, that will be included in here. We can use some complex form, so that we can introduce whatever their phase difference at the input. So, now we would like to emphasize that this directional coupler is lossless. We assumed there will be some kind of losses, but in this case we will be considering R square plus T square equal to 1. So, unitary operations takes place. However, there will be, in practical cases, there will be some losses. So, in that case whatever output you are getting here A naught, you just consider some kind of loss factor alpha into some kind of directional coupler length you can consider, then you can find whatever the loss is coming alpha at the end, whatever you are getting, you can consider that some losses are there that can be easily introduced. So, now we know that if we want to use this directional coupler for a known R T, you know that R equal to simply we can say cos times kappa L DC basically. So, that is actually R, and T also we have defined sine function of kappa L. So, to have a 3 dB splitting, this R and T, the mode of that is the absolute value of reflection coefficient, so called, whatever directly going and whatever crossing, they can be considered 1 over root 2. So, 1 over root 2 if you are just considering, then we can say that it will be a 3 dB power splitter. So, if you are just considering R equal to 1 over root 2, T equal to 1 over root 2, and then 1 over root 2, this can be written as, this matrix can be written as like this, 1 minus j 1, and 1 over root 2 is there here, everywhere. So, I have taken common factor. Now, if you see A naught, if I just write down like this, that will be this output, that is a superposition of whatever coming out of A input and whatever coming out of B input, that is the superposition you will see. So, whatever contributing to from B input, that will have some kind of pi by 2 phase shift here like this. Similarly, for B output here, I can express from this matrix directly we can get. So, if you just check carefully, in this case A naught B naught, whatever their original value was there, AI BI, along with that just additionally this directional coupler alone actually introducing some kind of phase difference, that is actually minus pi by 2 phase difference. If you see, if you take this one, for example, if you take this one A naught you can write something like this, minus j 1 over root 2 minus j AI plus BI. So, that means it is nothing but minus j equivalent to whatever you are getting like B naught. So, A and B naught also they are related, okay. They are related, but with a phase difference of minus j. Minus j means if you just put in phasor form, that will be actually j pi by 2, right. So, minus j pi by 2. So, that is how you get pi by 2 phase difference. So, the directional coupler, if you have input output, whatever phase initially difference there can be, but because of this the two outputs I am getting with a phase difference of minus pi by 2. So, that thing, because any integrated photonic devices or photonic integrated circuits, you have to handle superposition principle. So, in that case amplitude as well as phase both are important. So, now this is for 3 dB splitting, 3 dB splitting, that is the thing. But if you are just considering this directional coupler for complete coupling, that means if you launch here input here, so everything should come down to here, that means R should be equal to 0, right. And if you launch here, everything should be coupled here, that means there also R star should be 0. So, we consider for complete coupling R equal to 0, T equal to 1, that means transmission completely happens. So, in that case your this transfer matrix can be written as, so minus j 0 1 1 0. So, we know that that will be actually only off diagonal matrix will be there, T equal to 1 we are putting, T star equal to 1, R equal to 0, R star equal to 0. So, that is 0 0 is sitting here, and since plus minus j is there, minus j I can factor, okay. So, minus j if I factor here, then I can get what is A naught? A naught will be equal to minus j B I and B naught equal to minus j A I. So, that means now you see this minus j here also there, output A, output B also minus j. That means I can write down in phasor form A naught equal to B I e to the power minus j pi by 2. So, whatever it is there going there, along with that it is introducing pi by 2 phase difference, minus pi by 2, adding pi by 2, and here also whatever coming here, it is adding pi by 2 phase difference. But as a whole, if you just compare A naught B naught, if you compare their phase difference because of the directional coupler, because you see that there is no phase difference, because this is also minus j pi by 2, minus j pi by 2. So, they do not have additional phase difference because of the directional coupler, but both are having some kind of phase, they are identical phase. So, that is why the directional coupler in this type of situation does not introduce any phase difference between these two output ports, okay, because we are considering both input and both output. Good. So, this is the directional coupler, all we need to know to use to construct more advanced complex photonic integrated circuit or integrated optical circuits. So, let us try to see this type of configuration. You just imagine a Magenta interferometer constructed by help of two identical directional coupler acting as 3 dB power splitters. So, this is also 3 dB power splitter, this is also 3 dB power splitters, and two exactly identical directional coupler, meaning this waveguide and this waveguide, they are also identical, this waveguide also identical, their gap also identical, their length also identical, and it is adjusted such that both act as a 3 dB power splitter. We know what is the transfer function of a 3 dB power splitter, just few moments before we discussed that. You just connect them using two straight waveguide, identical straight waveguide, L1 equal to L0 and L2 equal to L0, And these waveguides and these waveguides, they are identical. You can assume that they are propagation constant, they support only single mode fundamental mode, and their propagation constants are beta same, identical. So, if this type of structure if you can construct, they are called balanced Magenta interferometer, 3 dB power splitter, 3 dB power splitter, and both the arms connected here, they are like a Magenta interferometer arms. So, you can imagine when we consider Magenta interferometer using Y junction, there also we have one input, split it into two, again combine using Y junctions. Here also you can, if you want to use one as input, suppose you are launching here, then 3 dB power splitter gives here 50% here along with their phases, and then this arm and this arm, they propagate with the same identical path, and then you can combine with another directional coupler. The process, you can use input here or here. So, you have two options, two input ports, one of them you can use, both of them you can use also whenever necessary. So, similarly here also both outputs are there, we can see. So, you remember that whenever we consider 1:1 Magenta interferometer using Y junction, so the power, if their phase difference between two arms is pi, then the power, entire power you are launching, that will be completely lost to the substrate. But in this case, it will not be lost to the substrate, rather that power, lost power can be appeared in the other waveguides, other output ports, that we will see. Okay. Now, our intention is that if you have inputs at both the arms, they can be complex, they can have some kind of initial phase difference and with amplitude, known amplitude, and you are launching there. And now, I would like to know what is the things you supposed to get at the output. If you can derive some kind of transfer matrix for this entire structure, that means A naught, B naught should be 2 by 2 matrix multiplied by A I and B I. Then you can use some linear algebra for constructing more advanced photonic integrated circuits using this type of structures. This is a very important structure useful for large scale integration of programmable photonic integrated circuits as well. Okay. So, our intention is to fill this matrix elements. So, what will be here A11, A12 and A21, A22, these 4 elements, if we know, if we can just construct, then it would be very good. That is what our intention. So, now let us annotate this entire structure into 3 zones, zone 1, zone 2, zone 3. So, this is basically we can consider directional coupler where inputs are same AI, BI, and just output section, if you see, that will be A1 and B1 we annotate. And this A1 and B1 we can consider that is the input for the arms, Magenta interferometer arms. You are launching here B1 and you are launching here A1, right. And then they will propagate L0 length, it will propagate also L0 length. Then you have at the output, after traveling, it can have some kind of loss, it can acquire some phases. We are considering lossless case. At the end, we can just calculate, estimate the loss budget. So, here this will be output A2 and B2. Only we can just consider now whatever the phase related information it is being carried as it propagates through the device or components. Now, you have third section, that is also 3 dB power splitter. We can say that in this 3 dB power splitter you have A2 input, B2 input into input ports and you are getting output ports. So, I know how to construct transfer matrix for this, I know how to construct transfer matrix for this, and accordingly I can say that this is splitter 1 can be written as 3 dB power splitter 1 by root 2, that is just a while ago we have discussed 3 dB power splitter. So, your inputs are AI, BI, then outputs will be A1, B1. So, we can write simply splitter 1 transfer function. Okay. Similarly, splitter 2, your inputs are A2 and B2, outputs are A0 and B0. So, we can write A0, B0 in terms of A2, B2, use another transfer matrix for 3 dB power splitter. So, straightforward. Now, let us consider what happens in between here. So, after reaching here, A1 becomes A2. How they are becoming A1? And since it is a propagation constant of the waveguide B and length is L0, so you will acquire some phase e to the power minus j beta L0. Similarly, B1 B1 convert into B2, how? With a phase, additional phase. Remember that it is like when it propagates e to the power j omega t minus beta z, that same thing we are considering, and we are not considering the field mode profile distribution. Instead, we consider that is actually normalized only the amplitude. That is just to keep you in mind. Okay, you must not forget that what is actually we consider for waveguide and for analyzing different type of components. So, I can say that A1 will become A2 and B1 will become B2, and this omega t term, because all frequencies are same, we can any point we want to know what is the time dependent variation, you have to just multiply e to the power j omega t. So, we do not consider there that e to the power j omega t, we are assuming that it is a monochromatic operation, Fourier domain analysis is happening. Okay. So, now in this case, if I want to write down these two equations in a matrix form, how it will be written? So, your A2, B2 will be output, I have written, A1, B1 will be the input. So, if you see, if you just use this type of matrix, then you see A2 equal to A1 e to the power minus j beta 0. So, A2 you will get this equation and B2 you will get this equation. So, these two equation you can write down in a 2 by 2 matrix transfer function here, e to the power minus j beta L0, e to the power minus j beta. They are identical, balanced terms, similar. So, now what we can do? We can say that this we can little bit modify, because 0 0 of diagonal elements we can write 1 e to the power minus j beta L0, it is a kind of factor I can take. So, you know, any system 2 by 2 system, if you see that some common factor is there in phase factor e to the power minus j beta L0, that it is not so important for analyzing the entire circuit, because both the output will have same amplitude, same phase. A1 will also acquire same phase and become A2, B1 also acquires same phase and becomes B2. So, if they are phase identical phase, that is not so important for further interference. So, that is why this one we can drop. In principle, that should carry by the both arm, but we can drop because of simplification. So, ultimately the T arms, I can say that the transfer matrix for the Mach gender interferometric arms, that means both the arms in short can be written like this. So, this is your 1 1 0 0, we can write A2 B2, you can write that one. E to the power minus j beta L not common, so we are ignoring, you must keep in mind that. Okay. So, as long as we are restricting your discussion with this two field only, and their phase factor, common phase factor, you can always eliminate, that is useless, because always that phase factor, common phase factor, if you can eliminate, only their time dependent. Similarly, whenever we are just considering this phase factor also, we are eliminating from the both arms, because they are same in phase, same phase in time. Okay. So, we constructed another matrix. We knew that TSP1 is this one, this is the matrix, and this is the matrix for 3 dB power splitter. Now, the central region also we have the matrix, okay, 2 by 2 matrix. So, what we can do, central region, you see I have this one TSP2 relates A0 B0, that means output in terms of A to B2. So, this A to B2, instead of A to B2 I can write this one, I can write this one, instead of A to B2 I have just written this one. So, that means this one TSP2 and T arms if you multiply, that means I can relate A1 B1. If we know A1 B1, then I know what is A0 B0. However, A1 B1 also we can relate with AI and BI with this. So, if I use this one and if I just bring this one to here, right, A1 instead of A1 B1 I will be writing this one, then what we get? We get this one. So, I use this one and then I say first this one was there, this one is there, instead of A1 B1 I am just writing this one. So, basically this expression comes here. Okay. So, I have now 3 matrices. Okay. So, this matrix corresponding to TSP1, that means this one, this is TSP1, and then middle one the arm, and then this one the final one. Okay. So, you start like this, if I just follow this one, you just total thing I am writing A0 B0, that means output in terms of AI BI, and I have 3 matrices. You see it is a order, whenever you are just considering AI BI, you are writing AI BI and then TSP1, the matrix comes here TSP1, and then AI in the left side you just add the matrix of the Magenta arms, this one, and then next you get this matrix output splitter TSP2. So, this is TSP2. So, that means if I want to relate input to output, and if we are using the matrices for individual components, what is the transfer matrix, then normally you should keep in mind that whenever you are writing, you want to know A naught B naught output in terms of AI BI we are writing, and then starting from AI BI next matrix I will be just entering here TSP1, and then immediately after AI BI you have this matrix, then this matrix is there, then this matrix will be there, and then left hand side you will be getting the. So, now if we just multiply this one, if you know, if you have different matrix to be multiplied, you have to again multiply them from right to left. So, you have to multiply this to this first, and whatever you get result, that will be again multiplied by this to this. So, that is simple matrix algebra. So, if we do that, so first if we just multiply this one, this to this, 1 over root 2, 1 over root 2 will be there. This one if you multiply here, basically nothing happens, 1 1 minus j, because it is diagonal unitary matrix, diagonally 1 1 is there. So, basically you are getting like this, and then if you multiply this 2, then you get this one. So, if you just multiply 1 by 1 over root 2, 1 by over root 2, it is there, and this one if you multiply 1 minus j, 1 minus j, 1 minus j, minus j 1, minus j 1, 1 minus j. So, simple matrix multiplication you do, then you get this one. So, minus 2j you can factor here, because both the element, all the elements are having minus 2j factor. So, we take and root 2 cancel, then what we will get, minus j common, and ultimately you are getting off diagonal elements are there 1 and 1, and minus j will be common factor. So, now I know this is going to be the transfer matrix for the entire structure, because all these transfer matrix together it is coming like that. Okay. So, what we do, we can drop this again minus j common phrase, e to the power minus j pi by 2, that type of things will be there phase. So, that I can drop, that will be appearing in both the output ports A naught and B naught, that is I can drop, then I will be getting A naught B naught can be related to only this central portion minus j common factor removed, and then we can just put that this one will be 0 and this one will be 1 and this one will be 1, this will be 0. So, I now know what is the transfer matrix for the balanced Magenta interferometer. So far so good. So, that is very useful. And then here what we would like to see one more interesting thing, that if you just see A naught equal to A naught will be 0 1 multiplied by, that will be B I input pi by 2. That means A naught, what you will be getting, whatever you are launching here, entire thing will be appearing here, but along with that pi by 2 phase shift, phase difference will be there. Similarly, if I launch here something like that, entire thing will be coming here with a phase shift of minus j by pi 2. So, they will be crossing each other. This system actually giving the entire structure gives you that the power, they actually switch their path. So, AI can be, I can just route, this type of structure can be useful to just routing from one branch to another branch. This is one waveguide is there, now I get another waveguide, so that entire power can be routed this side, and whatever you are launching here we can just cross them. So, this can be a good crossing in this integrated circuit. So, if you want to just cross the path from one structure to another structure, you can use this type of structure also just to cross the path, and of course, you have to bear whatever the insertion loss you are supposed to get there. Okay, fine. So, now what is the conclusion here? Again we say that it is something like that, it is 3 dB power splitter. Instead of 3 dB power splitter, directional coupler, if you have a LC length, then you know if you are launching in one side, it will completely coming back this side like this, right, and if you are launching here, it will be completely coming that. So, instead of 3 dB power splitter, as if these middle arms are not present. So, this 3 dB connect back to back, then you get normally the a 3 dB power splitter doubled the length. So, that means it is just crossing. So, the presence of the magenta arms in between, that is actually useless. Okay. So, that is actually we can say that this is something structure we get just connecting the directional coupler, though we call it is a Magenta interferometer, ultimately it is nothing but a directional coupler of length LC, cross coupling completely happens, and in that case two output ports will not have any phase difference. But if you just consider this one cancelled, only this one you are launching, then this one you will not get anything, this will be equal to 0, but here whatever it will appear, it will acquire with a pi by 2 phase difference. Similarly, if you are launching this one, this is cancelled, so everything will come here, but additional phase, whatever path related phase will be there, that is there, but in addition to that, because of this all this crossing happening, so that will create additional pi by 2 phase difference individually. So, that thing you should keep in mind whenever you are using this type of structure. This is straightforward, we are analyzing, easy to use. Okay. Now, so we have discussed over transfer function of the balanced MZI, right. So, we continue that, but same thing we continue, but this directional coupler in the both end, they are not identical. Balance, when we mean balanced Magenta interferometer, most of the time we refer that the arms are identical, but we do not bother about what is happening this directional coupler. We assume that they are typically 3 dB power splitters, but if they are not 3 dB power splitters, one of them may be 3 dB power splitter, another may not be 3 dB power splitter, you can get different type of functions. So, let us see how it will be going like that. So, as usual, normally if it is not 3 dB power splitter, you have this first directional coupler splitter 1 we consider, and that can be defined by R1 and T1. Okay. Matrix I can consider, that is through coupling is R1, cross coupling is T1. So, we can define the transfer matrix like this, such that it is lossless R1 square plus T1 square equal to 1. Similarly, TSP2 I can write here, this is not 3 dB power splitter, so I cannot write simply 1 by root 2 1 minus j 1 something like that. Instead of that R2 T2 I have just written, such that it is also lossless R2 square T2 square. And middle arm, as usual we can write middle arm will be, that is 0 1 0 0 1, that is earlier we have derived, that is same identical. So, if I want to see output to input, if I want to relate, then this is TSP1, this is Magenta arms, and this is TSP2 Magenta arms. So, we start from here to here, AI, BI, and then TSP1, and then T arms, then transfer function for the TSP2, we write that one. And then again we do matrix multiplication as usual I have done before. So, I just repeat that one, we just multiply this one, then we get this one, and then whatever the result we will be getting, we will multiply with that one, then we will be getting this one. So, matrix multiplication 1 to 1, you just multiply them. Just inspect carefully this matrix. You see again this one, this R1, R2, T1 star, T2, and this one if you see R1 star, R2 star minus T1, T2 star. That means whatever you get this element, this one is just complex conjugate of that one. R1, R2, R1 star, R2 star, T1 star complex conjugate T1, T2 complex conjugate T2 star. Similarly, this and this you consider, you get minus j T and minus j T star, whatever minus j, whatever multiplication is here, minus j complex conjugate multiplied here. So, it is as if you can write similarly, simply that entire structure can be written like this, that this is as a whole we are writing as a R, this one, this element I can write like a T, this element I can write a T star, this element I can write a R star. And considering these two and these two are assured, that means lossless R1 square plus T1 square equal to 1, R2 square T2 square equal to 1. They are not 3 dB power splitter, but whatever reflection coefficient, transmission coefficient, whatever goes there, reflection coefficient we call, transmission coefficient we call this one, and they are different, and we assumed this one, that has to be no loss is there. Here also if I try to see the determinant of this one, that means this one multiplied by this one and this one multiplied by this one, that means R square minus T square, that also will become 1. R square plus T square equal to 1. Okay. So, arms are lossless, we are considering 3 dB power splitter lossless, 3 dB power splitter lossless. So, whatever this thing we are getting, that is a simple like a 2 by 2 transfer matrix as if R minus JT, JT minus R square. So, that simply we are getting. So, that means if we are not using 3 dB power splitter, we also can find out a 2 by 2 matrix here, whatever the elements will be there, and we can find out if we know R1, R2 and R2, R1, T1, R2, T2, then we can find out what would be the value of these elements. This factor we can get the all the corresponding elements. So, that is a straightforward. As long as you know the transfer matrix, I think this is just a simple multiplications. But the interesting point is that there is no effective role of balanced MZI arms. So, if you see again, since they are identical, so ultimately this factor whether it is there or not does not matter. So, as if it is like a one directional coupler, another directional coupler back to back if you connect. So, that is the interesting point. One directional coupler and another directional coupler back to back if you connect, then the R1 cannot be considered like R1 equal to R2. R cannot be considered like this simply reflection coefficient, or simply you cannot just consider R1 R2, because you know reflection coefficient and transmission coefficient, if you are considering T1 T2, if you are considering T cannot be considered as simple T1 T2, just simple multiplication. Rather you have to find out this type of element. This will be your R and this will be your R star and this will be your T and this will be your T star. So, two directional coupler of non-identical coupling coefficients, if you just connect back to back, then you can find out the final transfer matrix in this form. So, the R can be just simply R1 R2 minus T1 star T2. It is not simply R1 plus R2 or R1 times R2, similarly T equal to T1 times T2, it is not like that. Suppose normally why I am saying that, suppose you have some element is there here and then another element is here, some wave is coming, then it is something transmitting T1 and then it is going there and this is say T2, then it will be, so ultimately the effective transmission coefficient is T1 T2. Simply we can say that whatever coming here, whatever coming here, it will be T1 T2. But in this case you cannot consider something like that because of the two ports. Because whatever coming here and another coming here and the nature of the directional coupler transfer matrix, you cannot just simply like the simply you cannot use R1 T1 and R2 T1 simply multiplications. Rather we have to use this one. This is the take home message. Cool. So, now we move on to discuss a bit another important integrated optical components, that is called unbalanced Magenta interferometer. So, why it is unbalanced? We will be using 3 dB power splitter, 3 dB power splitter. Instead of balanced arm, you are just considering, okay, the arm lengths are different, L1 not equal to L2, right. So, L1 I consider a fixed value L0 plus delta L by 2 and another arm, this is minus delta L by 2, such that L1 minus L2 equal to delta L. So, delta L is the path length difference between these two arms. So, just introducing path lengths, you will get a very interesting output. If there is no path length difference, we see that whether the arm Magenta interferometric arms are there or not, output is not going to change anything. It is like a simple one directional combined directional coupler, but you can find out based on their R1 R2 and R1 T1 and R2 T2 you can find out. But if unbalanced, how to proceed? So, this one the transfer matrix for the splitter 1 standard 3 dB power splitter. So, I have annotated same way A1 B1 output, whatever coming here A2 B2, that will be input to the second directional coupler. Okay. So, second directional coupler 3 dB power splitter I can write depending on the annotation here A2 B2 is the input, A0 B0 is the output, A0 B0 you can represent in terms of A2 B2. But in between, you know, I can say that A1 A2, that is actually you have A2 equal to A1 e to the power minus j beta L0 plus delta L by 2. that is the A1 A2 relationship, and B1 B2 relationship is the B2 equal to B1 e to the power minus j beta L naught minus delta L by 2. So, if I use this one, same way that phasor part is there, I just consider that the diagonal elements will be like that. Earlier we have used just e to the power minus j beta L naught in case of balanced arm, but in this case this L naught is changed to L naught plus delta L by 2, L naught minus delta L by 2 in the lower arm. So, I just use this one. So, if you proceed a bit more, so this one if you see, I can take e to the power minus j beta L naught common factor, then I will be getting e to the power minus j beta delta L by 2, and here e to the power j beta plus j beta delta L by 2. So, this is the thing. So, this was a common, I can drop out anything common factor in the matrix, because that will give you 2 by 2 matrix, that will eventually give you same phase in both the arms. So, that phase factor I can drop. So, I can use this is the this thing as a Magenta arms, Magenta interferometer unbalanced arms transfer matrix, I can write down that. So, note down that it is minus, it is plus, because it is plus is there, it is minus is there, accordingly you have written. Now, you follow that, you know now that this also you represented as a matrix form, this also you have represented as a matrix forms. So, A to B2 value, this entire thing I can represent here, and once we represent here, this A1 B1 I can put here, then I can get the final value. Okay. So, I just multiply this one, and then using this thing ultimately I am getting this 3 matrix, how they will be sequentially, the input AI BI, then input splitter 1, then Magenta arms matrix, and then splitter 2 I can use, and then we can get just simple straightforward that starting from there how I am getting just 3 multiplication I am doing, 3 matrix I have just written here, these 2 I have multiplied, I get this one 1 by root 2 this one, and then whatever result you are getting you multiply here 1 over root 2 1 over root 2, that will become 1 by 2, and this one will be there. If you just move on, you just simplify this one. After simplification, what you get, this minus j you take a common factor out. So, if you just take minus j common factor out, then you are getting a very nice transfer matrix, and which is actually A naught B naught relates to the input and output AI BI. So, now you know that what will be the element is this one. This one will be sin beta delta L by 2, and this one will be cos beta delta L by 2, and so on. 4 elements it is there, we can just enter here and we can get this is the ultimate transfer matrix. Okay. So, if it is an unbalanced case, obviously if you see that if delta L equal to 0, then what will be, you will be getting this matrix, you will be getting 0 1, and then this will be again 1, and this will be equal 0. So, that is actually balanced, it will convert into balanced one. So, this is a general form of transfer matrix for the Magenta arms. Okay. So, now unbalanced Magenta arm. Now, if you just consider one thing, suppose this BI, this value we are considering 0, nothing is there, this is cancelled. Okay. Just special case I am considering, and power I am launching at the input here as a AI square equal to Pi, that is the normalized power, that can be considered 1 watt, if not 1 watt, whatever power you can consider that one as if AI square. Okay. So, if that is the case, there this value I will be putting 0. Okay. So, if I put this one 0, then this comes like this, and little bit proceed, then what we get? We get one thing, the A naught will be sin beta delta L by 2 AI, and this one will be 0, and B naught will be this one. So, you see A naught will be sine function of delta L, and B naught will be cosine function of delta L. Beta is the propagation constant. Again, if you just put delta L equal to 0, that means balanced, then this one would become 0, A naught will become 0, and B naught will become AI. That means entire thing would come here if it is balanced one. So, this is the most general case. So, you can consider this one. Now, suppose nothing is launched here, and whatever the output output here at this point we can consider with respect to this input, whatever appearing here we consider this is a bar port, and with respect to this one this will be considered as a cross port. So, power at the bar port PB, power at the cross port we consider as a PC. So, PB will be A naught square and PC will be B naught square. So, A naught I have already got from this transfer function, transfer matrix. A naught is this one. So, PB will be this one square AI square equal to Pi. So, Pi times sine square beta delta L. So, once we know amplitude we can find out what is the power you will be achieving at the bar port and what will be the power at the cross port. So, if you see PB plus PC, they will be equal to Pi, because sine square same function, cosine square same function. So, lossless case, so total power is distributed. That means just if you change this delta L, if it can tune the delta L value, then depending on the delta L, one arm will be keep on increasing the power sine function. When this bar port, when it is maximum, cross port you will be getting 0 that time, and when you are getting cross port maximum, bar port you will be getting 0. So, this delta L actually give us a flexibility that if I design a unbalanced Magenta interferometer, if I want to get entire power maybe here, then delta L I can choose 0, and if I want the power to be distributed 50-50, I can just adjust delta L so that I can get 50-50. So, this delta L variations you can do actively or inactively or passively, that we will discuss later. For the moment you see that the output ports for a single input ports, output bar port and cross port, they are actually complementary to each other. One is a sine square function, another is a cosine square function. Total power remain constant. They are distributed among two output ports. Good. So, now reverse case we consider. Suppose this is AI equal to 0. I am launching entire power, input power at this port BI. Then this transfer matrix will convert like this. So, 0 AI equal to 0, BI 0. So, in that case output port A naught I will be getting here, that is cosine function, and B naught I will be getting minus sine function. So, now again with respect to this one I can consider this is cross port and this is bar port. So, in that case cross port I am getting here cosine function and bar port I am getting sine function. So, previous case it is sine square cosine bar and cross. Now, cross same thing it will be giving, I am just writing cross first, cosine function, sine function. So, they are actually simple, straightforward. So, once you know the transfer matrix, you know what is the power you will be getting, and depending on the delta L I can find out what is the value. Now, let us concentrate here. Suppose I want to get cross port maximum Pi and bar port 0. So that beta delta L by beta delta L, if I just consider 2m pi, then 2 cancelled, that means integer multiples of pi. That means integer multiples of pi, m equal to, m can be here, m can be 0, 1, 2, 3, 4, so on. So, if beta delta L equal to 2m pi, then I ensure that cross port will be maximum and bar port will be minimum 0, because beta delta L to m pi means sine pi by 2. So, you will be getting 0 here, and this function always you will be getting either pi, 2 pi, 3 pi, 4 pi and so on. If you continue, then you will be getting maximum here, and at the same time you will be getting minimum here. Okay. So, if this is the condition, if you somehow this delta L times whatever the path length difference if you introduce in the two arms multiplied by beta delta L, if that is exactly matching to 2 pi times integer values, then you can ensure that power, entire power, whatever you are considering here, that will be going to your cross port and other power will be in the bar port. If it is somehow beta delta, suppose beta delta L equal to, you are considering something 2n plus 1 pi by 2. So, if this type of condition is fulfilled, then you are ensuring that power will be always in the bar port, not in the cross port. So, if you fulfill this one, then power in the bar port. If you fulfill this one, then you get the power at the cross port. This is the two extreme cases. Now you see this beta You go back to our waveguide analysis, beta propagation constant, beta beta can be defined as omega by c, n effective index of the guided mode, and that can be written also 2 pi by lambda times n effective, and this n effective can be a function of omega, n effective can be a function of lambda for a given waveguide structure. So, I have just written this one, beta we know this one. So, beta equal to this one, and now here beta equal to, I can say 2 m pi by delta L. So, now I have omega by, I can write that omega by c n effective omega equal to 2 m pi by delta L. M is integer value, I know, constant, and n effective is a function of frequency, I know. So, now what we do this one derivative with respect to omega, because I want to see what happens to other frequency. This is the transfer matrix I am getting for a certain frequency. Beta is a function of frequency. If I tune my lambda, because I know I want to use this type of device for communication purpose, optical interconnect purpose. So, for optical interconnect I may have to use different wavelengths, I may have to use different channels, WDM, wavelength division multiplex systems, etc. So, if you just tune omega or lambda, omega and lambda relationship is 2 pi c by lambda, right, c is the velocity of light. So, if I just do derivative, what you get 1 by c, if I do omega derivative then it will be n effective, and then if I want to put omega as a constant and dn effective by d omega. Okay. I am just making derivative with respect to omega both side. Okay. So, if I detune omega, then right side what is going to change? Delta L is fixed, pi is fixed, 2 is fixed. Still if you want to consider, that means this m order must be changed. That means m equal to, we know that m equal to 0, 1, 2, 3, 4, so on. So, m must be changed. If I just vary the frequency here, make a derivative here in the left hand side, right hand side variable is m only, other things are constant. So, just m is the variation, but it is a quantized 1, 2, 3, 4, so on. So, in spite of that, if I just do derivative, left hand side gives me this one, that is what I have derived here, left hand side, and right hand side 2 pi by delta L I just constant fixed, and I just m I consider delta m, because it is a step type change can happen. So, I put instead of dm d omega I consider delta m delta omega. Now, you see the right hand side you concentrate, okay, 2 pi delta omega again you know 2 pi nu, okay, 2 pi nu. So, 2 pi nu, so if I put delta nu, 2 pi cancel, so 1 over delta L delta m by delta nu. Now, if I want to do one more interesting stuff, okay, this one if you just check carefully, we have derived earlier, that is nothing but the group index. N effective omega dn effective by d omega is the group index. If you are considering different wavelengths, different frequencies, then group index comes into picture. So, I just put here this one, then what I consider? If I put delta m equal to 1 and corresponding delta nu value, I define as a FSR. I will come to that point. Delta nu I just define delta nu FSR. So, 1 by delta nu FSR, then I will be I can find out delta nu FSR equal to c by ng delta L. That means, if I just change the order, this m by m plus 1 if I change, then my frequency change to satisfy this condition, that will be delta nu. So, that can be calculated as a delta nu FSR equal to, this one we are considering delta nu FSR, and this is ng by c, and delta L I have taken that side, okay, or delta nu FSR I take that side. So, I can just simplify it, delta nu FSR equal to c by ng delta L. So, what is this FSR? FSR is actually a very important term frequently used in photonics, particularly integrated optics and photonic integrated circuit. It is called free spectral range. So, why it is free spectral range? Because it is the, if I consider beta omega c, by n effective is equal to 2m pi. That means this is omega m. This is satisfying for a particular integer value. Now, if I go for another integer value m plus 1, I will get another solution for omega m plus 1, that will be 2 times m plus 1 pi. So, I will get another, because m is integer, I can run from 0, 1, 2, 3, 4 so on. So, that is why I can get a certain frequency, quantized frequency, where you can get PC maximum here. So, alternately if I just keep on changing frequency depending on the m value, certain frequency here you will be getting maximum, and at the same time once you get maximum here, PB will be minimum here. So, if you launch here and if you tune your lambda value, then a particular lambda, it matches it lambda or omega that satisfy this equation, you will get maximum power here and nothing will be here. Now, if you same device, if you change the frequency, change the wavelength, you can arrive to another particular wavelength in the next order when m equal to 1 m plus 1, then that wavelength will appear here. Okay. So, this type of device in principle you can actually demultiplex. If you have a 2 lambda value coming, lambda 1 and lambda 2, you adjust delta L such that 1 lambda can appear, it is satisfying this one, that means say omega by C n effective omega 1, C n effective equal to 2m pi, right, and another one I can write omega 2 by C n effective, that will be 2m plus, that is actual 2n plus 1 pi by 2. So, this thing if you just consider. So, omega 1 and omega 2, if you adjust such that this value it is coming odd integer multiple of pi by 2 and first frequency give odd integer multiple of 2 pi, then omega 1 will appear here and omega 2 will be appear here. Omega 1 means 2 pi c by lambda 1 will appear here and 2 pi c by lambda 2. So, 2 wavelength you can separate them. So, this unbalanced Magenta interferometer, it is a kind of device which you can actually design for wavelength demultiplexing. I will discuss that in the next lecture, how to design that demultiplexers, and sometimes it is called interlever structures. That means every alternate wavelength in a WDM communication system, you can actually separate into 2 branches. Okay, that is actually interlever. But thing is that I can design that free spectral range, so called delta nu FSR, that if one frequency is now it is appearing in cross port, then what will be the next frequency? I can say that if corresponding nu 1 equal to c by lambda 1, for example, you are considering, and the next wavelength will be next wavelength or the next frequency may be nu 1 plus delta nu FSR. So, that frequency again it will appear in the cross port. So, that is actually free spectral range. So, where you are getting maximum successive values, frequency maximum, if you just successive maximum value you are getting corresponding wavelength, you just subtract, that is actually called free spectral range for the balanced Magenta interferometer. Now, okay, in terms of this one, if delta nu you know nu equal to c by lambda. So, delta nu will be equal to minus c by lambda square delta lambda. So, delta nu, and if you just replace this one, you can find out in terms of delta lambda FSR, free spectral range in terms of wavelength, we can just derive. Cool. Now the last section, that is actually transfer function of a microring resonator, because all this balanced Magenta interferometer and unbalanced Magenta interferometer, and they are actually designed with the help of directional coupler. Same directional coupler, if you just a little bit engineer, you can actually get a very nice different new device, that is called microring resonator. Okay. We would like to introduce this microring resonator now, and we will try to find out what is its transfer function. So, you know this is a directional coupler, simple directional coupler, just 2 input AI, BI and A0, B0, and this first waveguide we just bring closer to the second waveguide to interact, to exchange power of a certain length, and we can again separate, decouple them. And this transfer matrix we can just define like this: R minus JT that R and T, all they are depending on the what is the coupling strength overlap of the fields and their length and their gap, all those type of things we discussed in the previous lecture, we know that. Now what you do, you see I have just structured our directional coupler in this form. What you do, whatever output you launch B1 here, for example, here you are launching and nothing you give here. Okay. Instead what you do, you know that something is going here. Instead of taking output here, you give a feedback directly here. So, the output of the cross port you bring back to give a feedback as a input. It is something like that positive feedback you are giving in a system. In electronic circuit, you know positive feedback. You just give output, tap a fraction of output and give it to the input. Okay. So, that positive feedback normally you know in electronics, that is a kind of oscillator design you do normally, electronic oscillator. So, here also you can think of an optical oscillator by giving a positive feedback. So, this type of structure I can just represent in this form. I have this BI input here and then you know this is a directional coupler, transfer matrix, and whatever coming here you get positive feedback and then it crosses here, and while crossing also little bit it can come back here and again it can circulate here. So, this type of structure is called Microring Resonator. Why it is resonator, it will be clear in course of time. But this is actually, you see, this is a simple modification of directional coupler. Output of the one of the output port, you are just giving feedback, positive feedback to the one of the input ports. So, basically directional coupler, it is constructed in this form called is Microring Resonator, and we know this one. And now we have to consider one more thing. So far we have been considering that directional coupler, Magenta interferometer, they are lossless, but ultimately waveguide will have some certain kind of losses as they propagate, right. So, while propagation some losses will be there, that loss we say that okay, you just get derive everything lossless, and at the end you can just estimate what is the link budget, loss budget for the entire structure, that is good enough. But in this type of when we are giving positive feedback, how much positive feedback you are giving, that you must know first, because there will be some losses is coming there while propagating, because whenever you are bending the waveguide structure, you know there will be some kind of if you have a waveguide, straight waveguide, and if you just slowly it is going like this smoothly, then almost no loss. But if you just want to make a quick shortening, quick bend of a structure, so in the bend region normally you can assume that there is a strong perturbation because of the bend induced perturbation, and that perturbation actually causes some kind of loss of orthogonality condition. So, power exchange can take place, guided mode can radiate power into leaky modes. So, some losses will be there. So, if it fundamental mode, if you launching here and then you sharply bend, so after that whatever you are getting here little bit in this region, it can happen that something will be lost. Apart from your defects related loss, just bend induced loss will be there, that cannot be ignored whenever you are making a very tight bending, just ring resonator type. So, you can assume that you annotate this is BI and this is AI you are getting as a feedback, and B naught and A naught. A naught when coming back to the directional coupler as a input AI. So, you know that you have a loss factor e to the power minus alpha L, and phase, this L is considered as the round trip total length of the perimeter of the ring. So, that is going like that. So, AI and A naught I can get a relationship, certain kind of relationship. So, in this type of structure, if you just carefully notice that we have one input and one output. BI is the input and B naught is the output. So, our intention is that what would be the value in terms of BI? Can I find a transfer matrix here like this which relates BI to B naught? And similarly, I would like to know in this case what is inside AI, what is there inside in steady state. You are launching light after certain time, what is the AI there in terms of BI? If I know BI, can I estimate what is the value of AI? Can I make another transfer matrix like this? So, that is our objective. It is very straightforward. If you know directional coupler, transfer matrix, it is a straightforward, you can just derive very quickly. I will just discuss that. Let us consider this thing. Now, you have this A naught and B naught, right. Now, simple standard directional coupler, I can write A naught and B naught. How is the relationship from here? A naught equal to, A naught will be R AI, this will contribute R AI, and something is contributing here, that will be minus JT BI. So, that is A naught I have written here. Similarly, B naught will be R star BI and whatever coming here minus JT star AI, that comes from this transfer matrix. Straightforward, two equations I am getting. And I am assuming this e to the power minus alpha L as A, that is called loss factor. We will call that as a loss factor. That means, what if I take a ratio A naught to AI, that is this is the loss factor is there. Other factor is phase. Phase factor normally don't contribute, it does not contribute to the power or intensity. So, I get these two equations. Let us move on. Now, you see A naught equal to AI e to the power j beta L. From here, if you see A naught equal to AI e to the power j beta L minus j beta L, that side will go A naught equal to, and e to the power minus alpha L we consider A. So, AI by A e to the power j beta L, that is what we have written. I just here I put O in terms of AI. If I just substitute, I put this one here. So, this equation comes like this, R AI minus JT BI. Now, this one from here, if you see this equation relates AI to BI. AI to BI, that is what our intention, AI to BI. So, I can just write AI equal to, I take this one, I represent this one, just eliminate AI in terms of BI, and A, beta, L, R, all these are known. We consider that R, T, R star, T star and beta, they are known from the waveguide characteristics, directional coupler characteristics. So, I relate AI to BI here from this equation, that is true, straightforward. Now, next thing is that use these two equations, this equation and this equation. If I eliminate AI, if I just substitute AI here, then I can represent B naught and BI. I can relate B naught to BI. That is what? B naught to BI, that is our intention. Whatever I am getting, B naught to BI. So, just comparing these two, I can relate B naught to BI. Just eliminate AI, substitute this AI value here. So, by substituting this one, I get this one. This is the ultimate results. So, B naught equal to this one maybe. So, this is the within bracket whatever I was looking for, that is nothing but you are getting this expression. Now, next thing is that I think without any loss of generality, I consider R equal to R star. Normally, you know R star, actually most of the directional coupler we can design, we get that reflection coefficient normally does not have any phase change, it can be real if we consider. Then this R star I can put R, right, and then we can say that T R equal to B naught by BI. B naught by BI is this one. So, this one if I put R is there already. So, you just simplify, you are getting this expression. So, this is you are looking for this structure, this what is the transfer. So, 1-to-1 device and this is your transfer function, amplitude transfer function by the way, because so far we are discussing amplitude transfer. So, if you want to know, if you know just reflection coefficient, reflectivity we can find out, just take a complex conjugate, right, transfer function, we consider transfer function of the ring resonator, R stands for ring resonator, ring, and take complex conjugate multiply, you get this one. That means, this is actually the power transfer characteristics. So, if you know this value, beta value, L value, R value, A value, then if you are just launching 1 watt, right, you just put down all these values, then you know how much power will be transmitted to the output here. So, this is amplitude transfer function that will be useful for simulating photonic integrated circuits using amplitude transfer function. And if you want to use that standalone ring resonator, if I want to know what is the input power and what is the output power, what is the change as a function of beta, beta means is a function of lambda, you can find out what is the output as a function of lambda, straightforward you can get. Similarly, if I just proceed from this one, I can have AI by BI. AI by BI, that relates how much it, and in the steady state how much you are getting all the time power here inside the cavity. AI or A naught, you can do that also. I am just considering AI. So, in steady state all the time how much field amplitude will be there just before the directional coupler here. So, that relation I get this one. Just take AI divided by E, and I say that transfer matrix, amplitude transfer matrix, is SR. SR means storage purpose. I am just considering stored inside the cavity, how much inside the ring, SR, and here transmission, TR. T stands for transmission, A stands for storage inside the cavity. Amplitude storage factor, we can say transmission function, like this. And this one again we can consider in the energy to storage enhancement inside the cavity. So, you take complex conjugate, multiply, then you get this one. So, this is interesting. You just look this one carefully. A is the loss factor, that means one round trip, how much it is losing to the outside world. R is the directional coupler property, how much it is coupling, self coupling. And you know that R square plus T square, basically this one also you just consider lossless directional coupler. You consider anything additional loss is there, that you can consider along with this e to the power minus alpha L, that part A you can consider. Okay. So, A is the round trip loss factor, we call A is the round trip loss factor, all these are known. Now, if we inspect, this is a only variable beta L. Beta L means omega by C n effective L. So, this omega means we can consider 2 pi C by lambda C n effective L. C cancels, so 2 pi by lambda n effective L, something like that. So, either omega or lambda, if I tune, I can change this beta L value, or I can change n effective, waveguide effective index, or I can change L. Let us consider that waveguide length, ring perimeter, and nature of the waveguide, that is fixed. Now, in our hand, if I tune the frequency lambda, then this beta L value will be changing. So, once it is changing, then this value inside the cavity, the power storage inside the cavity, energy storage inside the cavity, that is going to be changed as a function of beta L. So, this, since it is a cos beta L, as a function of beta, it is cosine function. So, cosine function you have plus, maximum is plus 1, minimum is minus 1. So, when it is plus 1, that means denominator will be minimum. When cos beta L is plus 1, then denominator is minimum, that means storage power will be more inside that, inside the cavity, ASR will be higher. So, when beta L equal to say 2 m pi, for example, m is the integer. If you beta you can tune because of the frequency tune or lambda tuning. So, if you can change your wavelength or frequency, then you can see that this cos beta L terms as a function of frequency or wavelength, it is changing as a cosine function. It can vary plus 1 to minus 1. So, that means when it is plus 1, you can say that that time inside that particular frequency, that particular wavelength, inside the energy storage will be more maximum, because denominator is a minus sign here. That particular condition is called resonance condition. So, we call it as a resonances when beta PL equal to 2 p pi. P is the integer, instead of m we are writing p. P can be 0, 1, 2, 3, 4, so on. So, if beta L pi equal to 2 p pi, then this value will become 1. 1 means denominator is minimum. Denominator minimum means SR will be maximum. So, that is the resonance condition, and that resonance condition, this will be 1, right. Then what you will be getting? A square 1 minus R square, and below denominator you will be A square 1 minus R square, and this will be 1 plus R square A square minus 2 RA. That is the maximum value. That is the resonance condition. So, at resonance, so you can find a wavelength. If you have a structure, you can find a wavelength or frequency, then that time your energy will be highest inside the cavity, and that is the resonance condition, and that at that resonance condition whatever value will be inside, that can be decided using this expression. If this ring is a lossless, that means A will be equal to 1. If A equal to 1, then what you are getting? 1 minus R square divided by 1 minus r whole square. That will be the fraction of energy will be stored inside the cavity, and that is the maximum possible energy, because we have satisfied this equation. If this equation is not satisfied, then inside energy will be started dropping. Okay. So, when it is started dropping, that will be actually appearing here, because we are considering lossless case, nowhere else lossing. If some loss is there, that will be lost also, that has to be counted, but other than that entire power will be coming out then. So, this is the resonance condition, where how we define resonance condition? The resonance condition is that condition where the particular input wavelength or light frequency that is in the transmission, that will be minimum. So, I know the transmission characteristics is this one, is defined by this one, earlier we have derived. So, I know that this is the resonance condition, beta L equal to 2 m pi. I can put here also beta L equal to 2 p pi. That means this will become 1, this will become 1. So, cosine function at resonance, I can say that r square, denominator will be r square plus a square minus 2ar, and numerator will be 1 plus r square a square minus 2ar. So, numerator and denominator, we know what would be the value at resonance. I just write down that one. So, at resonance, how much fraction of power will be stored and how much fraction of power will be transmitted, I know that. I can actually transmission, if you can design this ring resonator such that R equal to A, that means round trip loss is exactly equal to self coupling coefficient R equal to A. So, in that case the transmission will be completely 0, and here you will be getting R equal to A, that means you will be getting A square. So, that means whatever in the transmission you would get 0, whatever power you are launching here, something will be lost and something will be stored. Okay. So, that particular situation is called critical coupling. If it is not critical coupling, your transmission will be minimum, but your storage will be maximum when you fulfill this condition. That is a resonance condition, right. So, now we know that a ring resonator can be useful to store energy inside. You can use as a energy storage for a certain wavelength, certain frequency, and that storage can be available also in according to your demand, that we will discuss that later, but it is an important device. And again, you know, this expression, it is similar like that. If you change frequency, another wavelength also, because of p equal to 1 you will get one condition, p equal to 2 another condition, p. So, p is an integer. So, it is a not only one frequency, a series of frequency, discrete frequency, that will be resonant to this cavity resonator. So, I can find out the separation between two successive resonant frequencies, that will be again called as a free spectral range, what we have discussed while discussing the unbalanced Magenta interferometer. Okay. So, we can proceed same way. Okay, I have just written down everything in summary. So, this is the transfer matrix for the directional coupler, loss factor, and we have assumed R equal to R star, R square plus T square equal to 1, then amplitude storage fraction, that is defined by this one SR, that is AI by BI, AI that ratio with respect to BI, how much it is being enhanced inside the ring, and how much you are getting at the output B naught by BI, whatever B naught you are getting, whatever you are launched and whatever you are getting, that ratio I am getting. And then if you just consider how much energy or power stored inside the cavity and how much power being, fraction of power being transmitted, that can be derived like that. And at resonance, that is the condition, beta L equal to, here I have just again written m, it can be p or m, that should be fine. I think integer, as long as you are putting integer, that is fine. So, you are getting this expression at resonance. At resonance, transmission will be this one, that is so far we have derived. Now, if you see one thing you can consider, this beta again I am writing omega by c n effective L to m pi. Now, omega 2 pi c by lambda if you consider, then I can find out lambda m. So, these are the resonance, mth order resonance wavelength, right. So, if I say that lambda m is at L n effective adjusted such that I get lambda m equal to 1550 nanometer, and maybe m equal to 100, m will be 100, n effective if you put, suppose L equal to 100 micron, n effective equal to say 2.8 and L equal to 100 micron, into 10 to the power minus 6, and m I can find out, lambda I am putting 1550 nanometer, 10 to the power minus 9 meter. So, I can find out what is the order of resonance for this one I will be getting. Okay. Then this is mth order of resonance. So, now if it is little bit, if I change the 1550 to something else, I can find another integer which will be again resonance. Okay. So, that easily you can just find out. So, same way whatever I have just considered to find the FSR, free spectral range, there actually in case of unbalanced Magenta interferometer there is no resonance. There rather we are trying where is the maximum I am getting at the output. But here resonance means the wavelength where the energy storage will be maximum inside the cavity, inside the ring, and those frequency, that means difference between two successive frequency. If one frequency resonant at nu 1, another one is nu 2, for this m equal to some certain order and another is nu 3. So, it is actually nu 2 minus nu 1, that will be considered as a delta nu called free spectral range. Free spectral range that can be considered also C by NGL. So, here L is the perimeter length, and in case of balanced Magenta unbalanced Magenta interferometer, this L we are writing like a delta L, that how much difference between the arms that we are using. So, it is basically similar expression as that of unbalanced Magenta interferometer, but unbalanced Magenta interferometer, the power you are getting maximum in one port, the other port is minimum that time. When you are getting minimum in one port, other port is maximum. But in this case, when you are getting one particular frequency maximum, that means your output is port is this one, that maximum value is actually stored inside the ring. It is not taken out, it is not given out with other ports, because other ports actually in principle that is given as a feedback. So, this is a very very important device, and again this NG group index, depending on the group index I can find out, and if you carefully look this expression C by NG times L, C by NG may be considered as a group velocity by L, and you know this can be written as 1 over L by Vg. L is the perimeter length and Vg is the group velocity. So, perimeter length group velocity, perimeter length divided by group velocity, that means round trip travel time. So, that round trip travel time we can consider 1 over tau r t, round trip travel time of an information, of any message inside the ring. So, if you know that round trip travel time, if it is known, then you can find out free spectral range, or if you know the free spectral range, you know any information how much time it takes to travel one round trip inside the ring. So, this information we will be using for further advanced device design. I will just give some kind of hint here. So, all these background things whatever we have discussed here, that is very very important for optical signal processor design, because directional coupler, Magenta interferometer, Microring Resonator, these are the three passive components we use with different variants in their design for demonstrating different type of functionalities in photonic integrated circuits. I stop here today. Thank you very much.